Okay, everybody, we are going to take a look at 3.5. This is, I believe, the last section of Chapter 5 that we're going to go over. So let's get a move on. Complex numbers. So far we have looked at real numbers and we've looked at branches of real numbers, but we have not looked at imaginary numbers. When you put imaginary numbers with real numbers, you get the complex number system. So we're going to look at arithmetic operations on complex numbers, square roots of negative numbers, and complex solutions of quadratic equations. Now, the discriminant of a quadratic equation is negative, then it has no real solution. And we looked at this early on. For example, if I have x squared plus 4 equals 0, has no real solution because when we try to solve it, we get x equals plus or minus the square root of negative 4. But this is impossible since the square of any real number is positive. So negative 2 squared is a positive and 2 squared is a positive. So the negative numbers don't have real square roots. To make it possible for all quadratic equations, mathematicians invented and expanded the number system called the complex number system. And how they did that is they defined I as a number, and that number I is equal to the square root of negative 1. So this is a definition here. I equals the square root of negative 1. So that would mean if I took the square of both sides, then I would get I squared equals negative 1. Now the complex number is then a number in the form of a plus bi. So in other words, it can have a real part and an imaginary part. And a and b are real numbers. The I is the square root of negative 1. And we will look at some more examples. Definition of complex numbers is in the expression of a plus bi, where a and b are real numbers and I squared is equal to negative 1. The real part of this complex is a and the imaginary part is b. Now we say the imaginary part is b, but that is when it has an I with it. So two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Bottom line here is that this is considered a number. So the following are examples of complex numbers. This is considered a number. 3 is the real part, and 4 is the imaginary part because it has the I with it. The real part in the second one is 1/2, and the imaginary part is negative 2/3. Six I actually has a real part of 0 because you could put a 0 here and write 0 plus 6I. And this is also considered a complex number. Now, we didn't say that before because you didn't know about imaginary numbers. And the reason it can still be considered a complex number is we could have 7 plus 0I. Now let's look at arithmetic operations on complex numbers. Complex numbers are added, subtracted, multiplied, and divided just as we would any number in the form of a plus b times the square root of c. Thus, the only difference that we need to keep in mind is that I squared is equal to -1. Thus, the following calculations are valid. If you have an imaginary number times an imaginary number, then you would FOIL it like you would FOIL anything else, and you will have AC be the first, ADI, and that's where you get this right here. This is ADI. BCI, here's your BC with your I. And then finally, your last would be BI times DI is BI squared. Now, the important part here is looking at that I squared, because I squared is equal to -1. Now we have something that was imaginary being able to be equal to a real number, and this is why it was so important for imaginary numbers to be formed, because it has to fill in that gap. So now I have AC minus BD, because this is now minus BD. That's the real part. And AD plus BC is the imaginary part. So when we're adding and subtracting and multiplying and dividing, we'll look at addition. You're going to add together your real part and add together your imaginary part. Same with subtraction, but you have to remember that you have to distribute your negative through first. And then when you multiply, again, we notice that this minus BD is because we had that I squared. So we're going to express the following in the form of A plus BI. So if I take this first one and I'm adding them, I don't distribute any negatives because this is an addition sign. I want to add my real parts and add my imaginary parts. So here I have my 3 plus 4, and then I have my 5i minus 2i. When I simplify that, I will get 7 plus 3i. So this is now my number that I get from adding the two imaginary numbers up here. Now in B, when we go to the second one, we're going to notice that we have to distribute this negative through first. So once I distribute through the negative, I then am going to rearrange it, and my real part is 3 minus 4. And then my imaginary part is going to be 5. We have minus a negative 2, so 5 minus a negative, which will give me positive. And when I simplify that, I will get negative I plus 7i. Now in the next one, I am going to FOIL 3 times 4, 3 times negative 2i, 5i times 4, 5i times negative 2i. Now I need to simplify, and I will get 22 plus 14i. Now the last one, what we have to realize is that we have a pattern of 4s here, and I'm going to put this over here on the side because I really think it's important. First, we're going to have I, which is equal to the square root of -1. And then when I square both sides, I find out that I squared equals -1. Now, what would I cubed be? I'm going to move it over here to give me a little room because I have I cubed equaling I squared times I. Now you say, how do I get that? Well, it's a fact. If I have 3 i's here, that could be 2 and then 1. Well, I know that 2 is equal to -1, so now I can substitute -1 into this, and I have -1 times I, so I get -I. So far, I have I have I squared being equal to -1. I have I cubed equals -I. And finally, I'm going to look at I to the 4th. So I have I squared times I squared. Now, we know what I squared is equal to. Again, it's equal to -1. So now if I have -1 times -1, then that will give me a +1. So what I discover through this is that I have I to the 4th, and that's to the 4th. It's an I. It kind of looks like it's negative, but it's not. That's just the top of the I. Equaling 1. Okay? So these 4 combinations are super important for you to know. Okay? I equals -1. Square root of -1. I equals the square root of -1. I squared is equal to -1. I cubed is equal to -I. And I to the 4th is equal to 1. Now guess what's going to happen if you look at I to the 5th? If you look at I to the 5th, I to the 5th is going to equal I to the 4th times I. Now that I to the 4th is 1, so 1 times I is simply I. And this is where we see that it will repeat the pattern here. So the next one will be I to the 6th, which is I squared. The next one is I cubed, which is I to the 7th, and etc. So now the question is, if I have 23 i's, what I really want to know is what remainder would I have if I divided that by 4, because there's a pattern of 4 here. So I'm not even sure that I really like what they did right here, because they're just using it as the -1, but you can do it this way, and if you understand this, this is fine. But what I'm going to say is take that number 23, divide it by 4, and when I divide it by 4, it'll go in 5 times, and we really don't care how many times it will divide into the number. What we do care about is the remainder. And my remainder is 3. So this remainder right here tells me that if I have the 23rd, I'm really looking at reducing it down to I cubed. And I cubed is equal to -I. So you see here, you have I to the 23rd. You can divide the exponent by 4, look at the remainder, place that onto I, and then simplify it that way. Or you can do it as the slide shows. Let me get rid of this one right there, okay, as the slide shows. And the slide shows, take it down to an even number, and that's how many squareds you would have, 11 squareds, and that's -1. Since it's an odd number of times, it's still -1, and you have an I left over. Personally, I think this is more complicated, so my suggestion to you would be to just follow the exponent here, divide it by 4, take the remainder, and go from there. If you have any further questions with that, remember to ask me in class. Okay, so dividing complex numbers is like rationalizing the denominator of a radical expression. We call the complex number a complex conjugate if we have the number z equals a plus bi. Its conjugate would be a minus bi. So notice the a still remained positive. You didn't change it. So it's not the opposite. It's the conjugate. And what happens when you multiply a complex number by its conjugate is you will get a real solution. You won't have any i's that are left. So now what happens when you're dividing complex numbers? The first thing that you're going to want to do is look at your denominator and make sure you are multiplying the top and the bottom by the conjugate. So with that in mind, let's take a look here. What would I multiply the top and bottom of this by? One plus 2i. And then this as well. 1 plus 2i, because you have to multiply it by a form of 1. So the top and bottom have to be the same, otherwise you would be changing the value. So now when I'm multiplying this, I'm going to FOIL through the top, and then on the bottom, remember it turned to a difference of squares. So let's take a look at what happens. So here I have where I'm multiplying the top and bottom by the conjugate, like I showed you in a previous page. When I FOIL that, I will get 5 on the bottom. You might say, how did I get 5? Well, square this, square the 2, and add them together, because when you distribute this, you're going to have a negative and then an I squared, so it becomes a positive. So it's just 1 plus 4 on the bottom. And then you split it up. So now I have a complex conjugate. What if I just have 4i? I don't have a real number part. Well, again, the conjugate is the part of the imaginary that changes the sign, so it would be negative 4i. Okay, so therefore, here I have my 4i on the bottom is in my second problem. I'm going to multiply the top and bottom by negative 4i. When I distribute my negative 4i, I will get negative 28i minus 12i squared, which I squared is negative 1. So that's how I get my positive 12 in the front. Now you might say, well, why are we doing anything with that at all? And the reason that we are doing something with this is because we don't want that I in the denominator. Why? Because it's equal to the square root of negative 1. And remember, we don't have square roots on the bottom of a fraction. Now, square roots of a negative number. Just as every real positive r has 2 square roots, every negative number also has 2 square roots. So after you pull the I out, you are still going to have this plus or minus right here in front of it. Then notice if I square both of them, I will get I squared times r, which is negative I times the square root of r squared. And this is a proof that's just going back to show you that we have the negative r that was underneath the radical to begin with. So this is telling you anytime you have a negative r under the square root. Now we are only talking about square roots. We're not talking about cube roots. We're not talking about fourth power roots. We're talking about square roots. Negative r under the square root, you're going to take your I out, and I always tell everybody, take your eyes out, especially around Halloween when you're teaching this. Take the I out and leave the r inside. So the two square roots will be of negative r are I times r and negative I times r. Why? Again, because this is plus or minus I square roots of r. Now you might say, well, how come they didn't put plus or minus right there in the definition? Well, because a lot of times when we're just talking about one of the answers we want, it usually is just the positive. But here they're trying to show you that it could be positive I squared roots r or negative I squared roots r. The other thing which is important is when you are taking the i's out, you want to make sure you put it in front of the radical like this is. Because if you put it behind the radical, it could be confused as to being under the radical. Okay, so you want to make sure you put it in the front. Again, taking the I out. The square root of 1 is 1, so it's just I. If I take the I out underneath the square root of negative 16, I will have I times the square root of 16. Square root of 16 is 4. If I take it out from the square root of negative 3, I will have I square roots of 3. Now, when you are multiplying, you have to be careful because although you have square root of A times the square root of B being the square root of A times B, when it's negative, you have to make sure you take your I's out first. Okay? So always take the I's out first. So you always take your I's out first. So let's take a look at some examples. Here, if I have the square root of 2, the square root of negative 2 times the square root of negative 3, temptation is to multiply this and make it positive, but you have to take your I's out first. So first I have to take out my I here, and I have to take my I here. Why? Because if you don't, then you're ignoring the fact that it was in there to begin with. So now I times I is I squared, and then I squared is negative 1, so the actual answer is going to be negative the square root of 6. So these are not the same. You can't take this and then put them both under the square root and multiply them. You have to take the I's out first. Now we're going to look at some complex solutions of quadratic equations. Again, here's a quadratic formula. Hopefully by now you're remembering our song, x equals negative b plus or minus the square root b squared minus 4ac all over 2a. Hopefully by now you have that down. Anytime you have the discriminant, which is under the radical b squared minus 4ac, this part right here, anytime that is a negative, that means you're going to have an imaginary number or a complex number for an answer. So here are two examples. Then I'm going to subtract 9, take the square root of both sides. When I take my I out, then I take the square root of 9, and I get plus or minus 3i. So my answers are positive 3i and negative 3i. Now by the quadratic formula, I will come down and get a negative 4 under the square root, take my I out first, and then the square root of 4, and simplify that, and I will get negative 2 plus or minus I. Don't forget to distribute through this negative 2. From example 6, we see a quadratic equation with real coefficient has complex solutions. Then the solutions are complex conjugates of each other. So notice the last solution, we had a complex number, and the only difference between that and the other solution was that they were conjugates.